Okay, I think we are ready to start. Pascal is ready. I can see him, and the slides are ready. So let's get going. Welcome everyone. This I think is the third iOS Press Neurosymbolic AI Journal webinar. My name is Artur Garcez. I will be moderating today's webinar. It's a great pleasure to introduce Pascal Hitzler. Pascal is the Lloyd T. Smith Creativity and Engineering Professor at Kansas State University. He is director of the Center for AI and Data Science at KSU, and also the Institute for Digital Agriculture. Pascal is, of course, editor-in-chief of Neurosymbolic AI Journal, and he has more than 400 publications in the areas like theoretical computer science, machine learning, semantic web, of course, neurosymbolic integration, of course, and knowledge representation and reasoning. And Pascal and I go back a long way. I think we met for the first time at the beginning of the century when I visited him in Dresden. And today he will talk about neurosymbolic AI helping our understanding of hidden neuron activations. Thanks very much, Pascal, for giving the webinar. The virtual floor is yours.
Thanks a lot, Artur. And I think this is the first time you actually introduced me. So, kind of 20 plus years later. So, yeah, it made me smile. Thanks a lot. Cool. I wanted to mention here as an aside. So the name of my endowment, Lloyd T. Smith Creativity and Engineering Chair. I did not pick that, but I really love it. And Lloyd T. Smith, as I learned, was a Kansas inventor, I believe 150 years ago or so. And apparently that's still where the endowment comes from. So, but anyway, let's go to the talk. So I'll be presenting for about 40 minutes or so. Happy to take questions. Happy if you put them directly on the Slack. Or also for those watching this afterwards on YouTube, reach out on the Neurosymbolic Slack. And if you don't know how to find it, then please email me or Arthur or editors-in-chief of the Neurosymbolic AI Journal, and we'll add you to it. All right, so I'll be talking about neurosymbolic understanding of hidden neuron activations. And this is really something I've been looking at together with collaborators and PhD students for quite a few years. And it took quite a bit of time to kind of get where we are at the moment. I'll be telling you kind of the latest stages of this journey, including some stuff which I saw for the first time just a few days ago. Which we're submitting shortly. So, but before I do that, let's just look a little bit forwards and backwards. Well, this is the presence. Arthur already mentioned it, the Neurosymbolic Artificial Intelligence Journal, which we launched this year, and iOS Press is hosting this webinar series, and I'm really happy for all the support they gave in the past. And Arthur and I, and also Tarek Bezold, we are the editors-in-chief of that one. Also wanted to mention 2 books I edited recently on neurosymbolic artificial intelligence, which are attempting to capture a little bit of the state of the art of that currently very quickly developing and growing field. So pointers are here, or reach out if you need more precise pointers. The Neurosymbolic AI community Slack, which I already mentioned, has over 1,000 people by now, and the reason why we're not putting a join link public is simply because we want to keep out spammers. But a quick email will do to get you on it. All right. So now let's go back. Let's go back 20 years, and together with Artur, we started back then a workshop series on neurosymbolic learning and reasoning, which took place at major AI conferences almost every year since then. And that happened, of course, before neurosymbolic AI was really the thing it is today. Back then, it was a niche subject, with some dedicated people, but it was a small community. And that was, of course, also before deep learning. And that was one of the reasons really why things were so tough, in particular back then. Progress was really, really tricky because the artificial neural network approaches were just not powerful enough. Time has changed, of course. And right now we're seeing a steamroller on the topic, and that's rather great. If you want to have a glimpse at what it used to be back then, there's a link here to another book which I edited with Barbara Hammer. That's from 2007, and it gives you a pretty deep learning perspective, which is quite different from what we see these days. So, all right, but let's get to the substance of what I want to talk about. The context is explainable AI. So I'm interested in looking at, well, deep learning driven systems and making them, in a sense, self-explanatory, or explaining them post hoc after training, understanding why they make their decisions. And when I talk explainability, then for me, it's really about opening the black box. Because right now, what we have, deep learning systems, they are, well, intransparent. Well, we know, of course, what goes on inside. There's real values, they're chased along, and there's weighted sums and vectors and so on. Mathematically, it's clear. But in the end, it's a huge amount of neurons in there, a huge amount of weights which are being trained, and some activations flowing through that. And in the end, miraculously, we get, well, good results sometimes and bad results sometime else. And LLMs, for example, which of course is currently the big thing, which drives a lot of efforts, do fabulous things, for example, in terms of eloquence and grammar. And in terms of content, they sometimes just kind of do ridiculously hallucinate. And if we just had a way of understanding, well, what they internally understand or represent, then kind of that would be a big step forward. And of course, similar things for other neural network architectures would mean that we could have fail safes on what they do. We could present rationales to the user rather than just a decision. And the user could then kind of go back and say, well, does that rationale make sense for me? And we all know that, for example, going back to LLMs, just asking an LLM why it gave a response, that's not usually helpful, because whatever it may be telling may have nothing to do with actually what's going on internally in the system, because of course it has no introspective capability. So what I'm really interested in is this introspection, looking inside the neural network, trying to understand what do activation patterns mean inside there. And of course, this is a kind of risky undertaking because, well, how do we even know that what goes inside there can even be explained in terms which make sense for humans? Well, okay, well, we need to try. That's what we need to do. So, all right, another piece of motivation why we need explainability. And this is work by my colleague Lior Shamir from Kansas State. This is actually three different, but essentially the same type of experiment. So I'll explain the top left one, which is about COVID-19 detection from X-ray images. What he did was he took a benchmark with X-ray images of the chest, labeled COVID or no COVID, and as usual, you kind of leave a few out, take the rest for training your system. And it turns out he could train the system to an accuracy of 67% on the test images not previously shown. That's good, right? 67% is not bad. Now, here's the funny thing. He now took each of these images and cropped them. And he cropped them so much that only a little black square or gray square or whatever kind of grayish square from the background was visible. No chest on the image, no piece of the chest on the image. He kept the label, whether it came from a COVID or a non-COVID image, and then he trained a system with that. And the system still was able to detect COVID, although the chest was not there, right, with 62% accuracy on this benchmark. Chance accuracy would be 25%. So what's going on here? Obviously, the system is not learning code; it's learning something else. Yeah, and I mean, there's similar studies. Like, for example, I believe there's one well-known one where it turned out that the pictures of the ill patients, it wasn't COVID in that case. They had a kind of a watermark on the image which the thing picked up. In this case, we really don't know. And he did the same with gastrointestinal disease detection. He did the same with face recognition. It's the same result each time. You can train it without actually the object of interest being shown. Now, the point I'm making here is we have no idea what's going on. We would like to understand what's going on. How can we even start to understand what's going on? And while we are not doing exactly this scenario, it's somewhere on our future work line. It's a motivation for wanting to understand what are the neurons actually picking up, the internal ones. All right. So what's our approach? Our approach is the following, and I'm explaining that in a CNN scene classification scenario. So scene classification from images scenario, because that's kind of what we primarily looked at. We looked at some others as well, but we don't have that written up yet. So think you have a trained scene classifier. It's already trained. So in contrast to other explainability approaches, we do not require any specific architecture tuned to explainability. And that's also kind of nice, because usually the specific architectures mean you kind of accuracy gets lowered somewhat. So we don't need that. We just train our classifier just as you want to train the classifier. And then we want to look inside and explain what node activations mean. So for example, we look at a neuron. We can also look at examples of neurons. I'll come a little bit to that in a bit, but say we look at one neuron here in the dense layer, kind of late hidden layer. Then we can get two types of images that activate this neuron and images that do not activate this neuron. That gives us a positive set of images and a negative set of images. And then what we would like to know is what are kind of the commonalities of the positive instances that are not at the same time kind of properties of the negative instance. What are the commonalities here? And if we kind of find some way to find these commonalities, then we can call this a hypothesis for what the hidden neuron reacts to. Now, how do we get these hypotheses? And there's different ways how to do that. There's ways how to do this with unlabeled data. Specific interest in our case is doing this with labeled data, and we'll do a little bit of comparisons later. I'll talk about that in a bit. So we assume labeled data. We assume not only labeled data. In this particular case, the labels we have to the images are objects that are on the images. And then in addition to that, we have background knowledge. Background knowledge is essentially background knowledge pertaining to the objects on the images. So we have a knowledge base, and this is why it's a neurosymbolic approach, because now we're in the realm of symbolic artificial intelligence rather than in the realm of pure deep learning or artificial neural networks. So we assume we have a knowledge base. In our particular case, it will be a very large one, 2 million classes in a class hierarchy, but nothing more than a class hierarchy. That's not a principled restriction, but kind of for scalability reasons, we did it in this case. So we have a large class hierarchy. I'll talk about it in a bit. And then we use deductive reasoning, a deductive reasoning algorithm called concept induction, to kind of describe to us in logical form the set of kind of what the commonalities are between the positive instances that the negatives don't have. So, and now I'll need to explain to you a little bit more what concept induction does. I'll do that next, and then I'll talk a little bit about the background knowledge and about the data set, and then we'll come back to kind of how all this works together, and you'll see more examples. Concept induction next. All right. Concept induction. If you're familiar with inductive logic programming, then the one sentence explanation is concept induction is inductive logic programming carried over to another logic, namely to description logics. Description logics are decidable fragments of first order predicate logic, which are particularly prominently used in the context of semantic web data management, ontologies, knowledge graphs, these kind of things. So what it does, concept induction, is the following. You take a set of positive and a set of negative examples. I'm explaining this here in terms of a very old inductive logic programming benchmarks, namely Mikalski's trains. And we can do this with concept induction as well. So positive examples, the trains on the left, negative examples, the trains on the right. And think of these, the positive ones activate and the negatives don't, right? So that's the idea, essentially. And now we're looking for the commonalities of the positive examples that none of the negatives have. And if you look long enough, you'll find it. Namely, the commonality among the positive ones is that they all have a closed and short car or wagon, depending on the English-speaking country you're in, like this here or this here, while none of the negative ones have that. So of course, we want to get that using logical deduction. And actually, the inputs in this case are not given as images. The images are just for us humans to explain the example. The inputs are given in terms of essentially encoding as facts in a logic. And then you can also add background knowledge to this, of course, if you want. The result you get is in description logic, it's a classic expression like the one here. Which you can also understand as a set expression with a first order predicate logic formula in one free variable, for example. So that's what you get. That's the explanations you get. That's the things the positive examples have in common. That is the type of hypotheses we will get for what activates a hidden neuron. Okay, so this, by the way, is an example encoding for some of the trains. So this is what it looks like. It's fact, right, in a sense. And then you can also, as I said, add a background logic to that. All right. So how does the concept induction approach work? Well, just to give a specification, what happens is the following. You have a description logic knowledge base, that's the background knowledge, O, in description logic. So think of it first order predicate logic if you don't know what description logics are. We have two sets of instances, the positive and negative examples. And then we're looking for a class expression, an expression in one variable, such that S of A, meaning A falling under this class expression, is a logical consequence of the ontology for all positive examples, and is not a logical consequence S of B for all B being negative examples. That is the ideal case. Not always will such an S exist that you have for all and for none. In that case, you give approximations, like good approximations with some accuracy. How many of the positive or negative examples do you actually cover? That is logically how you specify what concept induction is. Now, the interesting thing, of course, is how do you do this algorithmically? Because this is expensive. So this is carrying over the idea of refinement operators from inductive logic programming. What you get is something like that described here. Let me not dig too much into details. You guess a solution, then you check how good the solution is. Then you do n minimal changes on the solution. Check which of the minimal changes does best, and then you continue with that and do another kind of set of minimal changes, check which ones does best, and so on. Then you do it in a systematic fashion, and you can start proving some guarantees that you may arrive at a solution if it exists or not, etc., depending on the logic. Now, one of the things that you need to do if you go that route is each time you check how good a solution is, you need to do deductive reasoning. You need to call a first order logic reasoner or description logic reasoner. And since you know how expensive that can be, because some of these logics are really, really bad in terms of computational complexity, that means you have a scalability problem if you want to look at a lot of things over a large knowledge base, etc., because it's just not scaling. So what we did to deal with that was we made a heuristic algorithm that was published at IIII 2019. And that heuristic algorithm essentially says, well, what are the restrictions? One of the restrictions is we have only a class hierarchy as background knowledge. Another one is that we do not get very complex formula as outputs. We essentially get single classes or conjunctions of classes as outputs. But at the same time, we can really scale up to a $2 million class background hierarchy. So, right, and that was an important step, which we had to solve before we could actually go to the problem at hand. So we were kind of a little bit stuck before we had. All right. So what do we use as background knowledge in our case? And then I'll come back to kind of the overview again. As background knowledge, well, of course, to start with, we wanted to look at a scenario that's manageable. So which is why we looked at the scene classification scenario, because we had a benchmark. I'll talk about it in a minute, which already had objects tagged on the images. So now we wanted a general purpose, but really large class hierarchy, which kind of made sense for this context. And in the end, we tried Sumo first. That's a kind of ontology with 25,000 objects, and it didn't actually work too well. And then the next thing we did is we curated the Wikipedia category hierarchy, which needed curating because it has loops, it's crowdsourced. So we heuristically curated it by removing loops, resulting in a class hierarchy of approximately 2 million concepts and with a broad coverage. And what I'm going to talk about, the results are obtained using this class hierarchy. All right, So back to the concrete setting. So we have the pieces now. We want to understand activations of neurons. We get positive and negative example sets. We have our background knowledge, which is that big class hierarchy, 2 million classes. We have our concept induction algorithm, which if we have the items annotated using information in the background knowledge, can give us commonalities of the positive instances, usually several responses listed by accuracy, by some type of accuracy measure. There's different ones you can choose, F measure or something else. So essentially, we now have the pieces in place other than the actual data set we're using in order to run our analysis. All right, so what's the data set? We take a scene recognition benchmark data set, the MIT 8020K data set, which is called 8020K because it has about 20,000 images. We did not look at all scenes, but just at 10 overlapping scenes, overlapping because we wanted to kind of have similar objects in different scenes because that would make the scenario more interesting for what we're trying to do. We trained ResNet 50 version 2 on this with a reasonably good training and validation accuracy. It was not important here that you really get to high accuracy, right? Because we want to analyze what the network does. That's the kind of main thing. We didn't try around a lot. So we did not try other scenes, for example, do the same thing. This is really the first thing we did, and this is what I'm reporting on. All right. So this is an example of an 8020K image. I think the scene here is outside warehouse or so. And they have annotation files, which actually carry quite a lot of information, and we throw almost all of that away. The only thing we keep is kind of this here. This image contains a road, a window, a door, a wheel, a sidewalk, and so on. And that's all we have. And that's what we keep for these images. And these identifiers here now, road, window, door, wheel, and so on, they're string matched to Wikipedia categories, which works rather well. Of course, you know, we all know there's probably errors somewhere and some of the matches are probably not working well. But this is what we did. And this is kind of what I based the results on. And they're encouraging, as you'll see in a minute. All right. So label hypothesis. So now we have all the pieces in place. This is just for completeness. That's the 10 scenarios we had: bathroom, bathroom, building facade, and so on. This is what happens. And I'll explain what happens by way of an example first before we dig into the data. So the example here is from a specific neuron. It's the second neuron in the 64 neuron dense layer of the convolutional neural network. It's neuron 1, so it's the second one. On the left are just whatever. You throw images out of the 8020K data set at the trained network. And then neuron 1 sometimes lights up and sometimes doesn't. So sometimes it gets activated, sometimes not. If it gets activated, we call these input images positive images. If it does not get activated, we call them negative images. Each image is annotated using the Wikipedia category hierarchy. And then we throw that into our heuristic concept induction system. And it pops out several responses. And the top response is crosswalk in this particular case. So I'm not making this up. This is really what it says. It says crosswalk. Now, crosswalk in this case is our hypothesis. It's our hypothesis for what neuron this neuron detects, or one of the things the neuron detects. Well, it's a hypothesis. We want to verify that hypothesis. First step is, well, do a crude verification. Now, we're kind of running out of pictures. We need a lot for training. 8020K has much more categories, so there's a lot of categories with only a few pictures. So we need new images. We go to Google Images. That's, of course, not ideal. We all know the problem with transferring deep learning to a new data set, but that's what we had to do. That's what we tried, and that's kind of how it worked, interestingly. So we went to Google Images. We used crosswalk as keyword to retrieve images. And here on the right, you see images which are retrieved using this crosswalk keyword. And then we can check, well, do these images really, or a majority of them, actually activate the neuron? And it turns out, you see neuron 1 pretty high up there, is that over 88% of the images, of the target images, that's what we call them, the images which we retrieved using crosswalk actually activate that neuron. So that's rather good, right? It isn't that high in all cases. Like For neuron 6, we had there's a dishcloth and a toaster on the image. Now, if we use that to get Google Images, the activation isn't that good. So this is our first step where we either confirm or not confirm the hypothesis. And rule of thumb, right? We said, what's a good cutoff? We said 80% is a good cutoff. If 80% of our retrieved images activate the neuron, then let's call it label confirmed. Okay. Now, I know that's still crude. That still needs more verification, but that's kind of what we did. And the bold-faced ones are the ones where we get a confirmed label. We actually get 20 confirmed labels out of the 64 neurons that way. And then we do an evaluation of this. The evaluation in this case now is a statistical evaluation. So what we do is we understand each row of the table which you've just seen, well, each bold-faced ones, as a hypothesis. So the hypothesis is now neuron 1 activates more strongly on crosswalk images than on other images. Then on images we retrieved using one of the other keywords. That's kind of what we did there, which we call the non-target images. So the null hypothesis would be there is no difference in activations. And then we can give a statistical analysis. However, we have to kind of face the fact that there is no reason to assume a normal distribution. So we need a test that works with that, which, for example, would be the Mann-Whitney-U test for assessment. And then we can do that. And what we get is this. So this here is the 20 neuron label pairs, which I called confirmed according to our 80% cutoff. And this now is the statistical analysis. And you see the p-values at the very end. 19 of those get confirmed with a value of a p-value of 0.05 or lower. Only one of them actually doesn't achieve that, which is the first one with building. All the others actually get that. And that's rather nice. So we indeed have a signal here. All right. It's not the end of the story. One thing here is that what we did when we calculated that is also look at how many of the non-target images actually activate the neuron. Like, for example, here neuron 16, for which the label was mountain and bushes, activates for about 25% of non-target images as well. Now, we can use this value to derive an a priori estimate of the uncertainty that we really have mountain bushes if mountain bushes fire up. I'll come to that in a minute. That's the new results, which are just hot off the press, right? But just to kind of give you the idea here, that's what we're trying to do. All right, I'll come back to that. Well, actually, here it is already. All right, so we did it a little bit smarter. So we did the following. We did not only just look at activation or non-activation, but we looked at, like, for example, for the neuron which reacts to central reservation, for example, we look at how strongly does this neuron actually activate if it sees an image. So does it activate kind of with just a bit, or with 20% or more of its maximum activation value, or with 40% or more, or with 60% or more of its activation value? The idea here was that the more strongly the neuron reacts, the more certain we could perhaps be, that's a guess, right? It's a hypothesis, that, well, it's really a central reservation, nothing else. And the data at first sight seems to bear this out. So, for example, in the greater 40% column, we have that the neuron fires only in 15% of the cases if there is no central reservation on the image. But if we look at greater 20%, so it activates with greater 20% in about 34% of the cases where the image does not have a central reservation. So the higher we have an activation, the more certain we can be that what we think has been detected really has been detected. What that gives rise to, essentially, is that whenever we can say central reservation detected or crosswalk detected because neuron 1 fired up, then we can give an error rate based on this static analysis, which we can do during analysis time, and present that to the user. And the user can essentially say, okay, so, well, okay, 14% error rate or whatever, 3% error rate. So now things get much more real, right? So that's the new results, and we actually did statistical analysis on this as well, which shows that, yeah, actually the error estimates we get that way are actually good in almost all cases. Paper coming soon. All right. Discussion. So we have signal. We have signal. We also have an error rate. I mean, that's cool, right? But let's look at some interesting examples. So type 1 and type 2 error is interesting in this case. So let's go back to our neuron 1, crosswalk. The first thing we did was we looked at images we retrieved using crosswalk from Google Images, which did not activate the neuron, right? So that's one of the, I always mix up type 1 and type 2 errors. It's one of those two. And here's an typical example of such images which did not activate the neuron, although they show a crosswalk. And what you see here is, interestingly, that 5 of these 6 images are actually computer graphics generated. None of the images in the 8820K dataset is computer graphics generated. So, kind of from that perspective, it probably makes sense. The last one, bottom right here, is also interesting because actually it doesn't show a crosswalk, or rather it shows a crosswalk by inference if you live in the right country, where you know that that sign means that underneath is a crosswalk, right? In other countries, you probably would say, what's that? Somebody walking on the beam or something like that. Oh, central reservation. There's a question in the chat. A central reservation is a kind of traffic island, I believe it's called in other countries. Some people call it a central reservation, a traffic island in the middle of the road. All right, so the other type of error, kind of whatever images retrieved using a different keyword than crosswalk, which actually activated the neuron, which we did not want to have activated. And here are typical examples for those. You see there's a prevalence of lines. You see there's one where there probably actually is a crosswalk. It was retrieved using a different keyword, perhaps the keyword hydrant, I don't know. But of course, it doesn't mean it cannot show a crosswalk. So our estimates are really, really kind of in our disfavor, but they still work. But there's another interesting thing here, because that's that a lot of these images actually show trees or bushes or brush. And I mentioned it earlier that when we do concept deduction analysis, we do not get only one response. We get several responses listed by some type of accuracy measure. And in fact, in this case, for our neuron 1, the third response from concept induction is bushes, bush. Actually, the second response is also crosswalk. That can happen. The third, so the next response is really bushes, bush, also with a very high accuracy score. We use something called coverage score in this case. It does not activate the neuron quite as much, right? But it still seems that, yeah, the neuron is sensitive to this. And yeah, we see that here. So, we're not at the end of the analysis because, of course, we could take the second and the third keyword into our analysis as well. And this is some of the things we're doing as we speak. All right, so this is all very encouraging. Another thing which we could do much more systematically but haven't done yet, we're currently in the process of automating our whole analysis pipeline to do things at better scale. So one of the things we could do is we could combine labels, explanation labels that are very similar. Like we have several skyscrapers in building here, in edifice skyscraper, for example. And so kind of we're not at the end of this. Of course, we can go forward quite a bit. All right, comparisons. And I'm aware of time, so I have a few more minutes. There's different ways how you can get the labels. In this case, we use concept induction, and this assumes that we have a scenario where we do not only have annotated inputs, but also background knowledge at our availability. There are approaches, of course, which would not need all of that. For example, there was a paper published last year, actually published at the time when we submitted our first version of the current work. Well, it's much more mature now, but back then, it was the clip dissect approach, where they essentially used a deep learning system, a pre-trained deep learning system, to detect the things on the images in some way. So this completely unlabeled data. You can also use the labeled data, but not use the symbolic algorithm, but just ask GPT-4, here are the things that are in the positive images. Here are the objects which are the negative ones. Tell me what the commonalities are for the positive objects. And of course, we looked into that as well, because these days you can't publish anything without looking at LLMs, it seems. So no, it was also instructive. It was interesting, of course. And it scales better than the concept deduction. And you don't need the background knowledge. You still need the labels. So these are staged in that sense. And then in terms of, so you have 3 different ways of producing labels. we have a statistical evaluation, which I showed you for the concept deduction piece. I'll show you a comparison in a minute. And there is another way how we can do an analysis that goes back to work by others called concept activation analysis. What they do there is essentially they take the whole hidden layer, take the concepts which were retrieved, whatever method used, and then we're trying to learn to detect those concepts based on this hidden layer activations. And if they manage to do that, then the concept is a valid concept. All right, so how do the comparisons pan out? Let me just skim forward here. So for each of the approaches, if we check the top 64 responses, because we have 64 hidden neurons in the dense layer, then out of the concept induction approach, we get 18 confirmed neuron labels. Out of the GPT-4 approach, we get 12. Out of the clip dissect, we get 5. So it seems that there's an advantage to going symbolic here, right? At least some advantage. There's, of course, also some disadvantages because you need labeled data and background knowledge, right? And a more extensive algorithm. But yeah, you get added value here. So depending on the scenario, that may actually be helpful. By the way, using GPT-4 was really just some prompt engineering we've done there. All right, so what about the different types of evaluation we can do? And here the situation is a bit inconclusive. Essentially, there's two different ways of concept activation analysis, CAR and CALV. One uses a linear classifier, another one uses a nonlinear one. So we looked at both, and then for each of them, we can compare concept induction versus, well, clip dissect, or concept induction versus GPT, or clip dissect versus GPT. And in most cases, the differences were not significant. There were only two which were significant. In one, clip dissect seemed to do better than GPT. And in the other one, concept deduction seemed to be doing better than GPT. That's the only very kind of slight indication. But yeah, let's put it that way. Concept deduction matches up with the other approaches. You could argue it does a little bit better, right? Now, this said, all of these approaches can be improved. There's scope for improvement on all of those, right? But it's important to also look at all of those and see where we get. There's another advantage to the concept induction approach, and that is that it is inherently explainable. It's a symbolic algorithm. You understand what's going on. You know how you arrive at the explanation labels. With neither of the other two, you get that. With either of the other two, you kind of get again a black box output for your explanation label, and you just have to kind of trust it, right? Or statistically assess it, like so. All right. So last thing I want to tell you in the 3 minutes I have is we did some assessments. This is actually 2 papers already. How well the different explanations, which we get through the different approaches, actually make sense for humans. The scenario is the same. It's kind of the images out of 80/20K. And what we do is we essentially make a human user study, and these look like this here. You give them 2 sets of images and then 2 sets of keywords, left and right, and you ask which of these better represents what the images in group A have that the images in group B do not. So that's the concept induction scenario, right? And now the question is, where do we get the keywords from? And there were 3 conditions in the original study, and then we added a 4th one in the new study, which is under review. The 3 in the original study were the following. One was concept induction results, the top 7 concept induction results. The second was a human-generated gold standard, humans kind of putting in keywords. And the third one was a quasi-random way of doing this. Quasi-random in this case was we took random images and then ran concept induction on them. That's what we did with quasi-random. So we had these 3 conditions which we pitted against each other. And the results were, well, the human gold standard, of course, was best. It was better than the concept induction results, and was also better than the quasi-random ones. But also, the concept induction results were clearly better in terms of making sense to humans than the random ones. So the concept induction results were somewhere in the middle here. And it was kind of expected. That was our hypothesis, really, that we would get that. But it's nice to have this confirmation. So we have this kind of verifiable approach here that can give us something that, yes, makes sense to humans. I mean, significantly more than kind of a quasi-random approach. this one here now is the new study. And here we added a fourth way of generating concepts, and that was by prompt engineering against GPT-4. And this is as interesting. So you may recall from the earlier one, the quantitative evaluation on kind of how many labels are we able to retrieve and how well do they do. GPT didn't do quite as well. We didn't get quite as many labels, and they didn't stand quite as well up to the concept activation analysis. However, if we asked kind of what makes sense for a human looking at the images in terms of explanation, it actually turned out that the large language model did better than concept induction. We also replicated human versus concept induction here, and again we're kind of confirmation humans do better. But we also looked at human versus the large language model, and human does better than the large language model. So the human gold standard is still better. Still, kind of there seems to be a trade-off here, right? The large language model seems to be able to produce labels that are more meaningful for the human, but the quantitative analysis, the correlation with what happens inside the dense layer is not as strong. So there's more work to do here, of course, but that's essentially where we are at the moment. All right. So, well, neurosymbolic approach works here. Symbolic methods are competitive, and at the same time, they're inherently explainable. It seems that we get added value out of labeled data in this setting compared to unlabeled data approaches. So if you have it, there may be an added value here. And of course, I already mentioned all presented approaches can be further refined. And yes, we're doing that. And in principle, there is no reason to think that what we've done here is restricted only to scene classification or only to convolutional neural networks. Of course, that should also work for other approaches. And of course, we're kind of this is in progress that we're looking at other scenarios as well. All right, I stop here. Thanks a lot. And if there's questions, we'll ask you to chat or on the Slack, or lift your hand and Artur will moderate.
Thank you, Pascal. Thanks very much. It's very important to see this line of research. We do need to try and make sense of the different networks and models that are out there now, having quite a strong impact in society and in our lives. I'll go first with a comment and a question, and maybe that will give the others some time. I think, yeah, like you said, they can just raise their virtual hand, and I think they can unmute and interact directly instead of using the chat. So yeah, you hit the nail in the head when you say that these LLMs, they give explanations, but that's fundamentally flawed, right? I mean, the idea that they will themselves come up with an explanation based on exactly the same system. So there has to be some new addition to that, and explainability will indeed be a key tool. I think in connection with some regulation to help people have more trust in these systems. But one thing that I'm seeing in the community more broadly is this distinction between human reasoning and formal reasoning becoming more and more necessary, because it's appealing, right? The idea of this system that is also providing some explanation. But it's and then people will refer to, well, that's what humans do also. They just provide an explanation, and that's what's happening there. We are just interacting with this system. So there is this need to ground things on formal reasoning, I think, as opposed to just the way that humans do it. So I was wondering if you can comment on that, and more specifically, so of course you're using formal reasoning through your use of description logics there, and more specifically, when it comes to the mapping that you had there, the example you gave, I think, was contains, right? You had a bunch of rules describing the contain relation in the images. I couldn't quite get whether those were given, provided, or there is a, the symbol grounding problem comes up again and again, right? When you connect your hierarchy, I'm not quite sure if it's a taxonomy or your hierarchy of classes there, which is provided symbolically with the images. And if you could say a bit more about that step, the connection between the images and the hierarchy or the ontology. Yeah, that's the bit I didn't quite get.
Well, I hope my queue is able to keep all your questions and kind of process them right. You have to remind me. So first on the reasoning. So I was at a really wonderful Dutch seminar last week on generalization by humans and machines. And I met there Wal Abd Al Majid, and he's kind of doing deep fake detection stuff like that. But one of the things he mentioned, I wanted to cite, and he said we have to distinguish between reasoning capabilities and reasoning-like capabilities. And large language models only have reasoning-like capabilities. And I just think that's completely astute. They don't reason. So let me tell you another interesting thing. I mean, there's all these anecdotes out there where large language models fail, right? And there's also tons of anecdotes out there where they fail whenever it has to do with any type of mathematical, aptitude, so to say. One of the things we did mostly for interest, we in that case, some collaborators of mine, Eugene Wasserman, my colleague, who's doing cybersecurity, and some others, some other students. We took a psychometric test for humans on numerical literacy and ran that against the large language model, GPT-4 in that case. And it turned out that the ability of the large language model to deal with this numerical literacy questions was almost smack on average human, right? On no matter how many runs we do. Now, average human is probably somewhere like, not quite end of high school, right? Because people, I guess, because some people don't, and some people tend to lose some things they actually learned in high school. So whatever, that's kind of roughly where I would put it. That's not a kind of authorized statement. That's kind of my feel for the types of questions there. Now, the interesting thing here, of course, is that humans, they score up to the very max. Some humans can do that. Some humans are really, really high scorers there, but the large language model is just kind of smack in the middle, and nothing else happening. And yeah, it's just an indicator, a kind of a formal indicator of what anecdotically is known already. They can't reason. They're stochastic parrots. They're really just stochastic parrots. And they do silly stuff simply because they don't even know where to generalize, right? And sometimes they think, all right, so kind of we make similar stuff. So the source text somewhere said Albert Einstein was born in Ulm, Germany, and the generalization maybe just replace another random city with it and say, well, was born in Cologne, right? Because you can generalize that, can't you? So that's just what they do. They're stochastic parrots, and we need explainability partly because of that, because an LLM is almost useless unless there's a human recipient or an automated algorithm which can kind of cross-check on the correctness. So that's essentially what we have there, in my opinion. So yes, reasoning is completely important. Reasoning in a reliability sense. Common sense reasoning is also very important, and there's still a lot of things we do not understand about kind of common sense reasoning can do wonderful stuff, of course, as well, because humans manage to really generalize in situations where on few examples, or in very vague situations, and do really well, which is something we just don't know how to kind of let machines do. So there's again a trade-off. There's different systems, and symbolic reasoning as the strong, really verifiable, provably correct reasoning has a place in this as well as its own type of reasoning. So I think they're all important in the end, and we need to look at how can we make them work together. that's that. The other question you had to do with
Contains the
with contains, right? Okay. So in principle, the concept induction approach can deal with arbitrary background knowledge. So of course, well, description logic, so you only have binary predicates, but you have restricted first order predicate logic formulas, particularly restricted quantifiers. In principle, it can work with all of those. Now, for the heuristics, we had to kind of simplify stuff. And one of the things we simplified, as mentioned, was we only have a class hierarchy in the background. So in a sense, simple rules. And then we also kind of simplified. I didn't mention that, but you of course found it. We simplified in terms of the binary predicates we had available, and said, well, okay, we essentially have only one, namely the one which states what are the things that are on an image, and we called that the contains predicate. And of course we made up the name for that predicate, but that was really just a one-to-one coming from the image annotations, which are provided with the benchmark. So the annotation said on this image is a door and a wheel and a truck. And we said, well, the image contains, right, a truck. Contains is probably a bad word here, but that's what we use. So this is all where that came from. In principle, you can do more complex things. You can use many relationships. You can use relationships in the background knowledge. But then you have to use a different concept induction system, like for example, DLearner, which is a sounding complete system. But then you cannot scale to so much background knowledge. So there's a trade-off here, currently at least. Again, something we need to look into. But excellent point.
Okay, thank you so much. Are there any questions?
Hi. I would like to ask a couple of questions.
Go ahead.
Thanks, Pascal. It was a very interesting talk. I was wondering about the sort of the analysis a little bit more. So have you looked into sort of what may distinguish high and low activation concept? So I know in some cases you had these examples where some neurons were very strongly aligned. In other cases, this is less so. Is there any, either theory or analysis or intuition here that you're aware of?
Thanks, Philip. Great you're here. Philip Lievsky was actually one of the organizers of the Daksha seminar I just mentioned, which was really a wonderful Daksha seminar. The short answer is we have not done that yet, but I'm very sure there's a ton of information and data. So here's one of the things I think. Right now, our analysis is mostly focused on single neurons and understanding activation of single neurons. That's quite unsatisfactory because, I mean, the whole value of artificial neural network approaches is that information can and mostly probably is very distributed, meaning that information, in a sense, is stored or present in the system by simultaneous firing of ensembles of neurons. And that actually should give you a much better read of what the network is detecting. Now we're aware of that, right? The problem with this to start with is that if you have 64 neurons in the dense layer, and that's only 64 neurons, right? That's not a lot. Then you have already 2 to the power 64 different subsets, which you can potentially analyze. So here you immediately have a scalability problem. And while we will not be able to do a full analysis, I'm sure we can do better than just looking at single neurons. But the first thing we need in place for that is an automated analysis pipeline, which essentially does the things I've showed you on the slide. And all that was kind of done manually, right? The retrieval was done manually, the feeding, the reading of whatever. Some of that was of course done automatically, but many of it was done manually. We need to automate this pipeline for us to be able to do a deep analysis on these type of things. And I think your hunch is completely correct, but I don't have the data yet. We will get the data. I hope, perhaps by the end of the summer, if you're lucky. So this is a really excellent point. Thanks a lot.
Thanks, Pascal.
Maybe Patrick would like to go next.
Hi, hey, Pascal. So I have a question, a couple of them. Did you do object or outline detection in when you were taking in the images?
So no, we did not. However, the clip dissect approach, well, I think the clip dissect approach actually uses. Okay, I may be saying something wrong here, but I think there is a object detection component, also something that utilizes captions which come with the images or so. So it's completely conceivable to look at object detection as well, as a way of as an intermediate step of producing explanation labels, right? So of course that's an option.
Right. I just keep thinking about your first example with the X-rays and so forth. If there's no object detection, then when the system is evaluating the images, it's evaluating the entire image, and it isn't looking at a crosswalk per se, because it's not picking out the object of the crosswalk out of the image. It's looking and then finding variations of black and white, but it could very easily be an apartments building with heavy patios, or and the reason that I'm saying that is, in trying to build cognition, you have to think. I can't think of any animal with eyes that only has one. And considering how difficult it is genetically to create two of anything, there must be a strong biological advantage to having depth perception and the ability to pull out objects. That has to be a fundamental property of cognition, and these images, unless they're doing edge detection and object detection, I think all we're doing really is getting a statistical answer for, well, this is probably the best match, but it's not actually seeing the objects or getting cognition.
So of course, I mean, the explanation categories do not necessarily have to be objects, right? And of course, in completely other scenarios where whatever you may be looking at text inputs, for example, for classification, it would be objects, it would be other things. For the example by Leor Shamir, right, which I mentioned at the beginning, the COVID X-ray, where you have just these gray squares. Of course, the question is kind of what's our search space for the explanations, and we would have to think of what a reasonable search space would be. And when we will start looking at this, using our machinery, and we will at some stage, then one of the things I would be looking at would be low-level image features, like whatever. What's the average tone, right? Tone and hue and color and all these kind of things. Are there any lines? What is the variance in color? And all these kind of things. So these could be looked at. But then also metadata, which we may know about the image. We may know something about the time of day where it was taken, for example. Perhaps there is a reason that sick patients, actually get their X-rays later versus earlier, right? Or it's a different X-ray machine because they need to be isolated, for example. And that is something that could be exposed using metadata which we have on the images.
Thank you.
And Taisa, I believe.
Yeah, Taisa, and I think we wrap up after that. Taisa?
Yeah. Hi, Pascal. Nice talk. I'm wondering, I know you've looked at kind of the statistical quantity of like, this is 80% activation or 70%. Have you, or do you have ideas of expanding that towards like kind of analyzing concepts that the network has found to be closely related, or kind of like some sensitivity in that space, if that makes sense?
So one hope here would be that the concept induction algorithm, in a sense, takes care of that. Now, of course, in our case right now, we only have a class hierarchy, but what it essentially does is if there's two things that are very close related, that would probably mean that they're both subclasses of some, not too high up upper class. And then the concept induction algorithm would tend to give you that more abstract class as the explanation, for example. So that's what the concept induction algorithm would do. And if you had not only a class hierarchy, but a real knowledge base, right, in the background, then it would tend to do that even more, right? So, but of course, it would be dependent on how your knowledge base is structured in the end. But that is something that really kind of hopefully would be captured by the algorithm here. It's good, very good point.
Okay. Thanks
a lot, and thanks for coming, Tyson.
Very quickly.
Great talk.
Yeah, thanks for your talk. Can I ask you a quick question? So you basically look at the dense layer, right?
Yes.
Is there a reason why you only look at the dense layer and the layers before, like other people do? Like people look at the filters.
So let me rephrase the question. The question is, why did we look at the dense layer first? Because that's really what we've been doing. Of course, this should not be restricted to the dense layer, and we do not want this to be restricted to the dense layer. However, digging manually through all this data is quite a bit of work, right? So this is kind of why we started dense layer, or where we started with just one layer. Now, why did we start with the dense layer? And the answer is we started with the dense layer because there's previous work already you're all familiar with, which already kind of indicate that the dense layer in convolutional neural network, seems to be talking sometimes about object categories. So other people kind of have had this indicator before, and that is why we said, well, okay, so we want to show that concept induction machinery works. And we do that in a scenario where other people have already found some signals, so we'll just find similar signals using this machinery. But that's really just because we need to start somewhere. And in a kind of laboratory way, you try to control a few of the variables in your first attempts to see whether things work out in principle before you kind of generalize from there. So that's really the whole story to that.
And you're aware of other methods like TCAP and network dissection and so on, where they look at filters and so on.
There's quite a few methods around there, and it's a huge space right now, right? And we'll need to look at kind of the mix of different things and remain reasonable in the sense of, I know sometimes people think you need to compare to everything else that's out there. So, but I'm aware there's stuff where
I'd like to just share one paper.
We do not have comparisons yet. So,
I'd like to just share one paper where they look at logical combinations of concepts. I don't know where you are aware of this paper, and that might be an interesting paper as a baseline for preparing your project.
So that rings a bell.
Yeah.
But if you can get a reference to me. Oh, you just posted it in the chat.
Yeah, just posted. Yeah,
all right. Thanks a lot. No, we'll look into that. Thanks a lot. So if that looks familiar, then we'll definitely have a look. Thanks a lot.
Great. Thank you so much. Thank you all for coming live. But of course, the recording will be available so many more people can watch. And thank you so much, Pascal, for giving your time. And I posted just a couple of links on the chat. One is about special issue calls and the journal, and the other one about the NESI conference in September. So you can have a look at those. So I think with that, we're going to stop here and close. And thanks, Pascal, again, and the organizers and at iOS Press. Thank you. See you at the next webinar.
Thanks. Bye-bye.